Hello, this is Eric from UNC Charlotte. Today, we will talk about abstract representations of parallel applications. In particular, we will talk about the most common representation, the parallel task graph. There are many abstract representations of parallel applications, and we will discuss the most common two. The parallel task graph representation is the most generally applicable. While most parallel systems are not programmed using this representation, it is the most commonly used to understand why an application achieves or does not achieve parallelism. This analysis is accomplished by looking at basic metrics that characterize a parallel task graph, and these metrics can be interpreted into how parallel the application actually is. A classic representation of parallel applications is the conflict graph. This representation applies when the tasks of the application can be executed in any order, but there are tasks that cannot be executed at the same time. This is typical in applications where two tasks may need a common resource which cannot be shared. Think of the problem of scheduling classes. Some classes require a particular instructor and a particular lab. Therefore, if two classes share the same instructor or the same lab, they cannot happen at the same time. This type of problem is typically modeled using a conflict graph. It is an undirected graph where each vertex represents a task, and two tasks are connected by an edge if they share a common resource. Scheduling the application in the least amount of time boils down to coloring the vertices of the graph with the fewest number of colors such that no two neighbors share the same color. In the example provided, there is a clear solution with 3 colors, and it is clear that the tasks 1, 2, and 5 prevent a solution that is more parallel. While finding the coloring of a conflict graph with the least number of colors is an NP-complete problem, there are good heuristics to solve the problem. Expressing the application in terms of a conflict graph can help understand how much parallelism is really in the application. The most applicable representation of parallel applications is the parallel task graph representation, sometimes abbreviated as PTG. Each task of the application is represented by a vertex in a directed graph. There is an edge between tasks X and Y if X needs to have completed before Y can start. For any valid application, there can be no cycle in the graph, or there would be a set of tasks which depend on their own completion. The mathematical object that represents the application is a directed acyclic graph, or DAG. In the example, task 3 cannot start before task 1 is complete, and task 18 will be the last task of the application. The tasks are associated with a processing time, such that Pi is the processing time of task I. Here, P7 is 10. The processing time of a task is the time that the processor takes to execute that task, and tasks are assumed to be purely sequential. We use the term processor in a generic sense. The processor could be a factory worker, an office clerk, a machine in a computing system, an actual CPU, or a core on that CPU. Depending on the precise context of the model, the vertices and edges of the graph could be associated with other characteristics. For instance, the volume of data between communicating tasks, or whether a task needs to be executed on a particular machine, such as one equipped with a GPU. The dependencies between the tasks in the graph come from hard constraints from the application. The example is actually a model of a recipe to bake a lemon pie. The yolk and the white of an egg need to be separated before the yolk can be mixed with sugar. Therefore, there will be a dependency between the task of separating the yolk and the white and mixing the yolks with sugar. We can see that there are 2 main parts in this recipe. The left part consists in making the pie crust, while the right part consists in making the filling. the two parts are mostly independent, though eventually the two parts are brought together. The PTG representation can be found in many applications that try to leverage parallelism. Compilers analyze the dependencies between instructions to reorder them to enable out-of-core execution and superscalar execution. SQL servers optimize the execution of queries by studying their internal structure to identify independent parts that can be simultaneously executed. Metagenomic analysis use the Galaxy framework to express the complexity of their calculation and deploy them on parallel machines. Enterprise-level project management use tasks and their dependencies to build project roadmaps. None of these applications directly think in terms of parallel task graph, but understanding how well the application or project performs requires modeling it as a parallel task graph and analyzing it. The simplest metric used to analyze a parallel task graph is the work of the application. It is simply the sum of the processing time of all the tasks in the application. It is often denoted as sum pi. In this application, the work is 107. The work is an important metric of a parallel task graph because it informs us of the sequential runtime of the application. Sequentially, making a lemon pie will take 107 units of time. Because there can be no superlinear speedup, we also know that on M processors, the application will take at least sum pi over M units of time. Using two processors, making the lemon pie will take at least 53.5 units of time, and probably more. The time it will take to execute the application on some number of processors is often called the max span. The work metric provides us a lower bound on the max span for any number of processors. The second metric that characterizes a parallel task graph is the width of the graph. It is the maximum number of independent tasks, of tasks that do not have a direct or transitive dependency. In graph theory terms, it is the length of the longest anti-chain. In lemon pie, task 1 and 3 have a direct dependency. Task 5 and 16 have a transitive dependency. The width of the graph of dependencies is the maximum number of tasks that do not have any dependencies between any of them. For instance, tasks 1, 2, and 7 do not have any dependencies between any of them. Therefore, the width of the graph is at least 3. Note that tasks 10 and 11 are also independent tasks. They have common predecessors, they have common successors, but there is no path from 10 to 11 or from 11 to 10, and that makes tasks 10 and 11 independent. Can you tell what is the width of this parallel task graph? Pause the video if you want to think about it. This graph has a width of 6, which comes from the set of independent tasks 1, 2, 7, 10, 11, and 14. Note that there is more than one set of 6 tasks which are independent. For instance, the set 3, 4, 7, 10, 11, and 14 is also a set of 6 tasks which are independent from each other. In this case, the width of the graph is given by tasks that are close to the root of the PTG. But we could imagine a diamond-shaped DAG, for instance, which would have one source and one sink, and lots of independent tasks in the middle. The width is important to know for a parallel application because that is the maximum number of tasks that could be executed at the same time. It imposes a hard threshold on how many processors can be useful to execute an application. On this graph, there is no point in using 10 processors. The width of the graph is 6, so at most we will only be able to use 6 processors. We are not saying that we should use 6 processors to execute this application. Any processor after the 6 is guaranteed to have no work to execute at all. We can identify the largest set of independent vertices in a graph using Dilworth's algorithm. It is a fairly complex algorithm that constructs a bipartite graph and extracts the width from a maximal matching on that graph. When done by hand, one usually estimates the width by trial and error. In cases, identifying a large set of independent tasks can help us understand the structure of the parallel application. The third metric that is used to characterize the parallelism of an application is the length of its critical path. The critical path is the longest chain of tasks in terms of processing time. The path 14, 15, 16, 18 is the chain of 4 tasks, but its length is 53 because it will take 53 units of time to execute. The length of the critical path is often denoted either as CP or as T infinite, since it is the time one would achieve by using an infinite number of processors. Can you find the critical path of this graph? Pause the video if you want to think about it. The critical path of the lemon pie application comes from the chain 7, 8, 17, 16, and 18. The length of that path is 73. Note that it is not the path with the most tasks, but it is the path with the longest sum of processing time. Whichever way the application is executed, that chain of length 73 will need to be executed sequentially. This is why the critical path is an important metric of a parallel application. It is a natural lower bound on the max span of the application. Even with an infinite number of processors, the critical path still needs to be executed sequentially. Mathematically, the level of a node is the length of the longest path that ends at that node. The level is recursively defined. If a vertex is a root of the DAG, its level is simply its processing time. If a vertex has predecessors, its level is its processing time plus the maximum level of its predecessors. Computing the critical path can be done in one pass over the graph. We start by marking all vertices without predecessors with their processing times. For a vertex without unmarked predecessors, we can compute its level by summing its processing time with the level of its predecessor with the highest level. We then mark that vertex and keep going until all vertices have been marked. Let's look at an example. At the beginning, all vertices are unmarked. All vertices are associated with the maximum level of their parent and with a level, both are initialized with 0. The algorithm picks a vertex that is unmarked. Here, it picks vertex 9 first by coloring it red. Its level is updated by summing its processing time with the maximum level of its parent. Then, each of its descendant is considered and their maximum parent level is updated. The vertex is then marked as done by coloring it gray. The process continues by picking another vertex. Here, the algorithm picks 1 next. The algorithm unfolds by considering the vertices one at a time. There is no particular order in which this process has to unfold, as long as a vertex is considered after its predecessors. Eventually, the entire DAG has been considered, and the vertex with the highest level will be the vertex that ends the critical path. One can then reconstruct the chain of tasks that form the critical path by tracing back the predecessor with highest level until a vertex without predecessor has been reached. We saw that parallel applications are often represented as a parallel task graph that expresses the dependencies between tasks. 3 metrics capture most of the characteristics of the parallelism of the application. The width indicates the maximum number of processors that could be used to execute the application. The work provides a lower bound on the best possible execution time, assuming linear speedup. The critical path is an absolute lower bound of how fast the application can get. Understanding these 3 metrics will help us analyze the parallelism inside an application.